So, hi folks, welcome to section 3. And here we'll be doing questions based on what you have learned in the previous sections. So, if you haven't watched the previous section, I highly recommend you to actually go and watch these. Without watching section 2, you won't be able to solve any of the problems discussed here. So, do go and watch section 2 first before attempting section 3. Also, before starting, I'd like to tell you that I'll want you before telling you the answers of every question we do, I want you guys to open your notebook and solve that problem. As we discussed in section 1, it's about the journey that teaches you more. That's what Drake says. Okay, so I'll highly suggest you guys to do that because that's like a process, and I know I've been at your place, and it's really a pain to do that, but still, just do it for just it's like a few minutes. It will really help you all. Okay, so let's start with section 3. Practice problem 1, we have a binary search. Imagine you're performing a binary search in a list of uh, 10 1024 numbers. What would be the worst case scenario for finding a specific number, and how many comparisons would it take in that worst case scenario? So imagine you have an array of about 1024 numbers. It could be any numbers from starting from anywhere, like maybe 50 to so on, or 1 to 1024. Now you need to find the worst case of finding a specific number. Imagine you need to find 97 in that. So what could be the worst case of finding that 97? Maybe like you are doing binary search and you're not getting the number, and you have to do a lot of iterations. You need to do I mean, by iterations you need to do a lot of comparisons. So what could be that worst case of finding, and how many comparisons would it take, and how many of the comparisons will consist of that worst case? The comparisons could be 9 comparisons, 7 comparisons, 10 comparisons, 15 comparisons. It could be anything. Also, this is like a bit tricky question, so maybe a lot of you won't be able to do it in the first place. So but still, open your notebook rather than doing it with these huge number of maybe you can open your code terminal and you can write some code and get the answer. Or you can open, and some folks even are good at maths and all, so they can actually do it. Logarithms are used here, so we'll discuss a basic definition that we actually studied in section 2. Okay, so take a minute and just try doing it. Okay, so let's jump to the answer. It's a bit tricky. It involves a bit of math, and maybe if like you guys are writing code, then you can actually get it easier than doing that math. But still, let's do it with the math. It clears our concept of binary search and its basic definition. Let me just keep myself in a bigger. Okay, you can read all of this stuff. This is very important, but for now, just for the sake of simplicity, I'll tell you how to calculate it. It's basically you just just doing a logarithm log to the base 2 of 1024. You just simply do this log to the base of 1024 here, and you will get 10. That is one of the basic definitions when we go for this binary search, because binary search, what it does is it just it divides your array into two parts, and this divide in while dividing all of these two parts, that's a mathematical concept when you actually divide. And the time complexity, you'll learn it in your future courses in college. But for a very brief example, if I were to tell you the best case, the worst case, all of these concepts are used in a specific a section of computer science known as space and time complexity. Time complexity is basically how much time an algorithm is taking to perform. And there could be like a lot of ways to do a problem, so there could be a way to solve a problem in a shorter way as compared to other one in a longer way. So the shorter one is more optimized. And the second one is space complexity, how much space or how much storage it is that algorithm is taking. It could be in MBs, it could be in KB. Some algorithms it's very fast but taking a lot of storage, so that is not optimal. And some of them are very slow but taking very less storage, so it's also not optimal. Depends upon the use case of what a specific person is looking forward to. Maybe a company is looking for something else, or a person or research is looking for something else. So not our case. So there you actually use it pretty well. So to find this specific answer, you just need to do log to the base 2 1024. You will get 10 as an answer, because log to the base 2 1024 is 10. You can do the anti-log as well, you'll get 10 again. So that's how you're gonna get the answer. You can read all of this stuff as well as you want to. And in case of any doubts, feel free to ask us in the WhatsApp groups or mail us in our specific email IDs. Let's move to the problem 2. In binary search activity, what situation represents the base case when searching through a list of 256 numbers? What is this base case crucial for? Why is this base case crucial for the efficiency of algorithm? Okay, so we have a binary search activity happening, and the situation is we have a list or an array, you can take any one of them, of 256 numbers. So, what would be the base case of it? I'll actually tell you, guys, you would have actually, while Pranay would be teaching you section 2, he would have, shown you the whole, like the distribution of, like a, what do you call it? A graphic where about binary search. So I would actually, if you would have noted that down in your notebook, I'll suggest you to refer that, or else you can actually, take a shorter array, maybe of 5 elements, and do the binary search on them, and then from there, if you can actually able to deduce why base case is important, then it could also work for you that way. You can always take a lot smaller example and do it as compared to not such long, like, so just to get a bit of a clarity. So give it like a go and we'll see the answer coming up in the next slide. Okay, so let's move on to the next slide. Let's see what's the answer is. Okay, so this is like a subjective question, not like an objective question which has a numeric value. So let me explain you why. In binary search, base case occur when algorithm is narrowed down to its single element and single constraint subset. I'll show you that graphic, that graph and all. This is what I was talking about, not the graph. Here, what actually is doing is just splitting the binary search into two parts. It's splitting the binary search in two parts. That's what I was actually telling you. So what happens is binary searches, you split, and that's how you actually do. And you will hit a base case where you can't split it more. This is a crucial, this is crucial as it starts the process in dividing and searching and determining whether the target is in the left side or the right side. Basically, what it's trying to say is imagine you have an array of numbers from 1 to 10 and you need to find number 9. So what you'll do, you'll divide the array. This is the first case, this is like the first half, this is the second half, and then you want to search a specific number 9. So 9 will be in second half because the first half has 1 to 5 and the second half has 6 to 10. So to get like your time complexity less, so you will start searching directly in the second half. So that's what this statement, this is crucial for, as it starts the process in dividing and searching the space. This is what it means. Choosing the right base case is it's key for algorithms efficiency, enabling elimination of half the possibilities with each guess. Imagine you are not splitting the array. Imagine you have to do every imagine you are not splitting the array, and then you have to actually go to each of the steps and you have to do, have to check each of the elements in an array on a list. So it is such an heavy time, like it's taking so much time, so much, like computational time. It's very expensive when it comes to that. If you're doing using normal for loop or while loop to do all of this stuff, you have to actually go to every element, check if this element is equal to key or equal to target or whatever you want to call that variable that you wanted to find out. This is so expensive. Rather than when binary searches does this, you have array, I'll just break it up and I'll just know, and I'll just do the searching in half of the parts. So it's like you're cutting like almost 50% of the time, and your base case actually help us to do this. So that's the importance of base case here in binary search. Problem number 3. I hope you got what I'm trying to say. Any case in any route, just feel free to ask us. We are very happy to explain you again, no matter. All we want is to, actually you guys should learn and be able to understand what recursion is truly. If let's move to the problem number 3. If the numbers in the list were arranged randomly instead of ascending order from 1 to 2048, how would this affect the efficiency of binary search? Interesting questions. All of you who have heard section 2 very clearly and have made notes will be very will like it's will very easily answer this without you don't have to spend time doing it on paper or writing code or something like that. It's one of the very basic stuff what binary search is. It's like one of the very basic definitions of binary search. Very simple question, but still the ones who have read it would be very easy for them to solve it. The ones who did, didn't remember what they actually learned in the last section, the best thing they can do is again take an array or a list of 5 and try doing it, randomly assigning it and trying doing a dry run or trying running that inside, or maybe writing code for that in your terminal and see what happens. Okay, try it, take some time. Okay, I hope you went through that hustle for doing it, and the ones who already know, voila. The answer is it would make the binary search impossible. The very basic of the definitions of binary search is that the array or the list should be sorted. If it's not sorted, then the binary search couldn't find out in which of the section and which of the halves my target value lives on or relies on. As I told you, in an array of 1 to 10 or a list of 1 to 10, you need to find number 9. So you already know the number 9 exists in the second half. 1 to 5 is the first half, 6 to 10 is the second half, and you need to just search in the second half just to find that number 9. Now imagine number 9 is on the third position of an array: 1, 3, 9, 7, 4, 2, 8, and something, and 10, and the other is like that. It's all jumbled. So imagine, even if you are just doing, like just dividing it up, you can't really find it out. So that's the problem with, like binary searches. The array should be sorted, or the list should be sorted. So this was the answer to this. I hope you guys get what I'm trying to say. In any case, if you're not getting, just try going to the section 2 again, and just going to the slides and all will give you a very good explanation. If not, if you have time, I would highly suggest you guys to actually go and listen to the lecture again. Practice problem 4. After performing the binary search for a specific number 3 times and still not finding it in a list of 5 and 2 numbers, what could be a possible reason to this? Okay, 512. I will suggest you guys to write code for this. You can, if you don't know like like the structure of the code, refer it to from the previous slides and try writing code for it. You will get your answer. You will get your answer. It's not a very difficult question. It's just about you trying to solve it up. Open your code terminal, open your code editor, and try solving this question on code. Don't do it on paper, because like the array is like 5 and 2 numbers. It's practically impossible to do it on your notebook. Give it a go. Very simple. Just need to replace the value of n in the same section that we actually gave you, the same code section we gave it in the last section. Very simple. Try doing it. Try giving it a shot. Okay, I hope you guys tried it. Let's move to the solution. Okay, if you even if after like doing and by doing the binary search, even after like 3 times you're not finding the number, the maximum possibility is that the number is not in the array or in the list. Because even if it's in the binary search, it would have actually found it out. But even if it's doing for 3 times, then it's near, like it's the number is not there for sure. For sure, it's not there. There could be some possibility if the array is very long, even longer than 5 by 2, but still in case here, the number is not there in the list. A very simple answer could actually been gotten very easily from code. So okay, so let's move to the next question. Okay, suppose you are halfway through a binary search and realize that you made a mistake in your last guess. How would you rectify this mistake and continue the search efficiently in a list of 1024 numbers? Again, a very interesting question. It requires more cognitive thinking. Open a notebook, or open a notebook. Try, trying to write, get the solution of this. Try writing some code for it. Try hustle a bit. We'll discuss the solution in just like a few minutes. Give it a shot. Pause the video now and try doing this. Okay, now let's move to the solution. Adjust the search area based on the corrected feedback. Okay, so this is one of the things that you actually have to, like this is not a conventional question that you are actually going to get. This question was majorly meant to actually, get your understanding on a very strong and take your understanding to a stronghold. So let's actually go through this whole bunch of text together so that you can actually explain it. I'll explain you each of the lines and all, so that we can actually, like go through it pretty well. If you realize that you made a mistake in your last guess during a binary search, you should adjust the search area based on the corrected feedback. Okay, this is like, okay, we said it. Now, what's this? This involves correcting the midpoint for the next guess and continuing the search efficiently from the adjusted positions. Okay, now imagine you did some mistake in in your previous step while doing binary search. Now, how will you suggest it? Binary search always happens, it always happens in a split. Imagine like every time in binary search there is going to be split happening, first half and second half. So anytime there is a mistake, you need to go to that midpoint, and that's the point where you have to do all your operations. That's the thing that you can, if you fix it, everything's going to be fine again. Okay, so there's no need to worry about it. You have to go to that midpoint again and you have to start solving this. Now, how to do it? Let's find out in the continuing the text. Starting the search again from the beginning, option A is unnecessary. Option A, this is like, could be like, I just divided it in options. Maybe you can actually tell you pretty well. I first gave options to these questions, but I thought if giving options would be very easy for you to guess and all. But still, let's do it. Searching again wouldn't do much of a thing. If you were to search again, you will stuck again. So it's unnecessary. It's time consuming. And it's like that's what not we do as a good programmer or a good coder or a good computer science students. We always value time and space complexity, as I told you in the previous section, so we'll do that. And continuing without adjusting may lead to incorrect results. As I told you, you need to adjust, you need to correct your midpoint, only then you can get the exact answer. And option D, asking help from someone else, is not a typically needed if mistake can be self-corrected. It's just like you can yourself solve the problem. There's no need to ask to anyone. And these kind of problems, this what we actually read, this whole text is going to help you a lot when you're solving complex data structures and algorithm problems. Maybe for your interview questions or maybe for some or the other project that you're trying to create. You will definitely encounter problems when like you made some or the other mistakes while writing the code, on maybe it's difficult to remember the syntax or something like that for or other like the function to make it happen. So make it like that way, so this thing will actually come to you very handy. So what you need to do basically, binary search, keep in mind, split is happening, everything happens, any mistake happens, it's maybe you need to fix that split, and that split happens at a midpoint. So that midpoint is the like the focal point, so you need to fix that. Okay. I hope you guys got it. This was like a bit different. I know this was all of this was new to you, but don't worry. Just keep going through. Don't worry. It's like everyone faces a bit of problem because it's the first time you're learning this. Don't worry, you will get to it. Don't worry. If you're not getting it, it's not a big deal. Don't worry. Okay, now we go to the merge sort questions. Interesting concept. I hope you guys learned it in the previous section. If not, please go it again. Watch. Let's go to the questions. Suppose you are given a list of 16 unsorted numbers and you are asked to sort them using merge sort algorithm. Which of the following describe the initial step of merge sort process? Selecting the middle element of the list, dividing the list into two halves, comparing adjacent elements and swapping if needed, repeatedly merging adjacent pairs of the elements. Very simple question, very typical merge sort question, easily answerable. Give it a go. Let's see if you can able to answer this or not. Try to think, try to like remember what you actually learned in the previous section. Okay, move to the next. Let's move to the next slide to see this answer. The right option is B, dividing the list into two equal halves. I'll show you the graphic again as I show you for binary search. For merge sort, I'll show you again. And this should be your like go-to stuff. This is merge sort. What is happening there in the first place? Array of numbers sorted in random order, placed in random order. What you do, you split it up from between two halves. That's the first step. That's the first step you do. The basic step is first splitting. That's what merge sort is. Keep this in your mind. I'm not just telling you to remember this or learn. You like just like just mug this up, but still just have a picture of this. What happens basically? This is like a very good graphic. It should be in your mind. It should be in your in your copy, or it should be written in a notebook. Okay, we came a bit far. Okay. Let's move to the next question. I hope you guys got it, what I'm trying to say. In a Mercer algorithm, what is the base case that stop the recursive splitting of the list? When the list is completely sorted, when the list is completely empty, when the list contains only one element, when the list is divided into two halves. Again, a very simple question. I showed you the previous image of merge sort again. You can actually get it from there. Think it and try doing this. Give it a go. Okay, so let's move to the answer. Very simple one. When the list only contains one element, that's our base case. You can't divide it. I'll show you the graphic again, don't worry. That's our go-to thing. See, here you divide it again into how, like blocks of 4 and 4 for just this specific example. Of this blocks of 4 or 4, you divide it again into two halves, 3, 7 and 3, 2 and 6. You divide it again into 1, 1, 7, 3, 2, 1. Now you can't divide 7 more because it's already one element. What will you divide? There you can't can't cut it, and all something like that couldn't happen. It's just one element. So that's our base case. Even every time writing the code, that's your base case. The moment you get the first element, you can't, like the last element or the single element, you stop there. That's your base case. That's where you write your return statement. You get out of the recursion. If not, then the recursion will go on. You can't stop it then. So let me just go to the problem. Option C, okay, when the list has only one element. I hope you guys got what I'm trying to say. Let's move to Okay, this was the end of the section. Also, I wanted to, before ending section, I wanted to tell you one thing. If you don't have the base case in your recursion, this is base. The recursion will go on forever. It's like basically the infinite loop that you actually have in for or while loop. It's like the loop is not terminating. The loop is going on forever, forever, forever because it has no base case. The recursion is calling itself. Like imagine there's like a block of code and there's this return statement of the recursion. Return anything and all. Maybe it could be normal recursion, something like that. So this recursion statement doesn't have a base case, so it just call the function again and it will run it again and again and again and again endless times, and it will eat up your memory eventually. So that's with it. So okay guys, I hope you actually learned a lot while going through this set of problems. We'll also give you problems to solve as a part of an assignment. So you have to do it. Before doing that, I will highly suggest you guys to go through all the problems that we do in this whole series of 1 to 5 sections, so that you can have a highest probability of solving them and getting the correct answer. And getting the correct answer is not the point, it's about understanding it the best. So thank you guys, take care, see you in the next section. Bye bye.